Assalamualaikum and hi semua. Okay, and a very good day to all of you. Right, I'm Shikin Aziz. So today we continue again for this recorded lecture material for the topics of vessel under external pressure and combined loading. This topic is covered under EPFO 801 Process Equipment Design. Okay, a subject for Bachelor of Process and Food Engineering, University Putra Malaysia. All right. So, uh, all right. The main reference for this textbook is taken from chemical engineering. The main reference for this lecture note is mainly taken from chemical engineering design principle, practice, and economics. Okay, and process design textbook, which is written by Towler and Sinon. Okay, so let's begin this lecture. All right. So for vessel subject to external pressure, okay. Uh, all right. So the example of this type of vessel, vessels that are operated under vacuum for maximum pressure 1 bar or 1 atm, or jacketed vessels. All right, a jacketed vessel where the inner vessel under the jacket pressure. All right. So for jacketed vessels, the maximum pressure different it should be taken as the full jacket pressure. Okay, due to sometimes it may arise in which the pressure in the inner vessel is lost. All right. So that is how the external pressure act upon the inner vessels. So a previous lecture I have shown the failure due to the external pressure. All right. You may refer to previous recorded lecture to see how external pressure can impact your pressured vessels. All right. And then thin wall vessels subject to external pressure are vulnerable to failure. All right, through elastic. All right, through elastic instability, or in other words, they call it buckling. All right, and it is this mode of failure that determines the wall thickness. Okay, which the wall thickness needed. All right, so method to determine wall thickness of vessel subject to external pressure is more complex actually, and this is not covered under the main textbook that we are using right now. All right. Um, ASME BPV Code Section 8 Division 1 Part UG 28 specifies the design method for cylindrical vessels. So if you do have this standard, we can refer based on this standard. All right. Okay, so for meantime, for this lecture content is using this chemical engineering textbook. Okay, this chemical engineering textbook. So I leave it like this for this lecture content. All right, and then while the SME BPV Code Section 8 Division 1 Part UG 33 specifies the design method for hemispherical vessel heads and other shape heads. So generally, vessels that are subject to external pressure are normally reinforced with internal stiffening rings. Okay, there is another structure in the vessels that you need to consider. And the method for sizing the stiffening ring can as well be referred from the ASME BPV code. Okay. All right. Then for consideration of vessel subject to combined loading, okay, most of the vessel has a combined loading. All right. Um, okay. So you must make sure your design can withstand the loading, okay, the loading without failure. So um, this is example. This is the list of combined loading that might occur. All right. Uh, on the vessel. Okay. All right. So we do have here maximum weight of vessel and content under operating conditions. Under operating condition. All right. And then maximum weight of the vessel and content under hydraulic test. And we have wind loads, design pressure, including the static head of liquid, and earthquake seismic, and external loads, which imposed by piping and attachment equipment and other equipment. So, right. Then let's look on the weight loads. Okay, let's look on the weight loads. All right. So the major sources of dead weight loads are vessel shell, all right, vessel shell, vessel fittings, okay, for example, the manways, nozzles, internal fittings, for example, like plates, okay, the plate plus the fluid on the plates, and heating, cooling coils, and then external fittings, okay, such as ladders, platforms, piping, insulations, right? And then the weight of liquid, okay, the weight of liquid which is fills in the vessel. Sometimes the water is filled in the vessel for the hydraulic pressure test, and it as well may fill with processed liquid, okay, okay, then due to misoperation. Sorry. So, so the weight loads, okay, for the weight of a cylindrical vessel, okay, um, the weight of the vessel and fittings, okay, can be calculated from the preliminary design sketch, okay. So where the weight of the standard vessel component may include heads, uh, shell plates, manways, branches, and nozzles. All right. And then these components, okay, these components can be the weight of each of standard components can be referred from where did I put it? From Megacy, okay, Megacy 2008 and Brocknell Young, okay, all right. So you can refer this in order to use a standard weight for these components, all right. Well, okay. Well, for preliminary calculation, okay, you can approximate the weight of cylindrical vessel with dome ends, okay, with dome ends, dome end, and with uniform wall thickness and excluding internal fitting. So we can assume this: the vessel with dome and uniform wall thickness and excluding internal fittings. All right, this is as a approximation, preliminary approximation. So we can use this equation. All right. So this equation require some parameters such as here, as you can see here, the weight loads unit is Newton, and then you need a factor for the weight of manways, nozzles, internal supports. Okay, for example, we use 1.08 for vessel with a few internal fittings, and we use a factor of 1.15 for distillation column with plate support rings or equivalent fitting manways. And then we need a density of vessel material, and then it based on the textbook, it advised to be double for sealing attachment, for sealing, attachment fitting, and moisture absorption. Okay, to consider this. And then while the height height or length, okay, in meter, and this is the unit for the density, okay, for this equation. And then the mean diameter. So for the mean diameter, alright, it's actually internal diameter plus the wall thickness, alright, and then wall thickness and gravitational acceleration, alright. While for steel, okay, for a steel vessel, okay, the equation is reduced into these simplified equations, right? And then the values, okay, there are some values being listed in the textbook. Okay, these values, okay, can be taken from Nelson. Okay, this reference. Okay, so there are some values that can be used, okay, as a rough idea, okay, as for a preliminary. Right, so we do have a weight of fitting like cage ladder, plain ladder, platform, contacting plates, and the density for material. All right, foam glass, mineral wool, fiberglass, calcium silicate. All right, and then and these densities, as I said just now, it should be double to allow for attachment fittings. Okay, if let's say you have fittings and sealing, okay, right. Then for wind loads, okay, so it's important for you to know that for tall vessel, okay, when it is installed in an open area outside of the premise, all right, when it's under wind loading, all right, especially for freestanding vessel, okay, for freestanding vessel which mounted on the skirt support only and not attached to structural steel, can act like a cantilever beam. Okay, it can act like a cantilever beam. All right. So this illustration, okay, shows and is the illustration for cantilever beam. So if we the beam, okay, right, this is an illustration to show that our tall vessel can act like this cantilever beam. All right, and then the bending moment for a uniformly loaded cantilever, all right, you may use this this equation. All right, and where x is distant from the free end, okay, the distance from the free end, and w is a load per unit length. All right. So basically, right, the tall columns, okay, for the tall columns, the bending stress due to the wind loading will often be greater than direct stress, okay, due to pressure, and and then this will determine the plate thickness needed, and then the most economical design will be where the plate thickness is progressively, okay, the plate thickness, right, the plate thickness is progressively increased, right, the plate thickness is progressively increased, all right, increase from the top, okay, sorry, the plate thickness is progressively increased, sorry class, um okay, is progressively increased from the top, from the top to the base of the column, okay, so the thickness will be increased, all right, from the top to the bottom. Okay, progressively increase. So basically, what I understand is this the bottom part will be thicker. Alright, the thickness will be thicker, and the thickness at the top being sufficient for the pressure load, for the pressure load, and at the base sufficient for the pressure plus the maximum bending moment. Alright, so so and then so at the column base, alright, at the column base, this area, at the column base, this area, okay, the bending moment the how to say the bending moment due to concentrated load can be represented by this equation. Okay, can represent by this equation. And then where FP is local concentrated load at the top here. Alright. Okay, FP. Alright. And HP is the height of the concentrated load. Concentrated load above the column base. Okay, above the column base. Alright. So basically this is to show that any local increase in the column area, okay, in the column area which is presented to the wind will give rise to a local, alright, to a local. So it's also known as concentrated load, okay, alright. So this is to show the concentrated load at the local area. Okay. Then for dynamic wind pressure, okay, dynamic wind pressure, okay, the load acting on any structure by the action of the wind, okay, is actually depend on the shape of the structure and the wind velocity. Thus, it is represented by this. It can represent by this expression for the wind pressure, where if you refer this CD, okay, CD is actually a shape factor. Alright, it will depend on the structure. Okay, the shape of the structure, which is shape of your column, and then density of air, and then a wind velocity. Okay, so it's good to consider the maximum velocity that might present at the site of the construction. Alright, okay. The drag coefficient is alright. The drag coefficient is a function of the shape. Okay, due to why it's present like this is due to the drag coefficient. Okay, as it's a function of the shape of structure and the wind velocity. Where for smooth cylindrical column, okay, for smooth cylindrical column or stack, you may use this wind pressure expression. And then factor should be increased. Okay, there is a factor here. Original equation are using factor of 0.05, and this factor be increased to 0.07 for column outline, which is broken up by attachment. Okay, for let's say your column outline, there is installation of pipework or ladder, so you need to increase, okay, this factor to increase the strength of your design. And then you may refer this reference, okay, Engineering Sciences Data Unit, Wind Engineering Series, to provide detail of data and design method, okay, for wind loading, okay, for wind loading, designing and considering this wind loading. And then so a column must be designed. You must make sure that when you design a column, it must design to withstand the highest wind speed. All right. So and then uh, that may be that may be accounted at the site. Okay. Throughout. I mean, sorry, during the life of the plant, and then how to get this information of wind speed. Okay, you may refer a record or record from meteorological records. Okay, for the site location. So nowadays it's not so difficult because we do have weather forecast website. So maybe from there you can get the data. You can extract some data, history data from previous years, and then you can get a profile of the wind profile at the site. Okay, you can get profile for the wind. Okay, the wind situation at that site. All right. So uh, and and then uh, okay, then and then for the wind load the loading. Okay, the loading per unit length of the column. Okay, the loading per unit length of the column can be expressed by multiplying uh, wind pressure by effective column diameter. And then this effective column diameter is actually outside diameter plus allowance for thermal insulation and attachments. All right. So uh, you may use 0.4 meter for allowance for cage ladder. Okay, for cage ladder. All right. Then, when considering a wind load, you will need as well to consider deflection. Okay, deflection of tall column. All right. So the allowable deflection is actually around less than 150 millimeter per 30 meters of height. And then the formula of deflection of uniformly loaded cantilever, you can use can use it. Okay, the formula for this in order to calculate can be used for column with a uniform thickness. All right. So if your column is if your you design a column with uniform wall thickness, you can simply use a general equation for uniformly loaded cantilever, the cantilever equation, all right, to calculate the deflection of the cantilever beam. All right. For there are example of this. All right. You can go to this website. Uh, all right. You can go to this website. Okay. There is a list of a series of equation how to calculate the what is it? The deflection, maximum deflection. So here is an example of okay example calculations for cantilever beam with uniform distributed loads. So you may calculate the maximum reaction, all right, reaction of force, the maximum force, and then you may get the maximum moment, and then you can calculate maximum deflection. And here the equation has been embedded in the calculator, all right, where you can simply put the your parameters, all right, or your variable, and then you just click calculate, all right. But of course you must know what the equation for your project design, okay, to enhance your understanding, to ensure that you really understand how this equation works. All right. Okay, then if let's say your wall thickness is not constant, okay, it happen, it common for design, where if where there are certain part of at the column have a different wall thickness, in order to increase the strength of the vessels, and then the calculations, the formula can be taken from this reference. All right, and then this is not covered for this lecture material, right? Then for wind loads, okay, for wind loads, the sorry, for the wind induced vibration, I'm sorry for that, for wind induced vibration, you must know that wind can create a vibration, and then this vibration can cause damage to the vessel, to the column, due to resonant oscillation, okay, oscillations. So basically, when frequency of shedding of eddies is equal to natural frequency of the column, it will cause premature failure, okay, of the vessel by fatigue. So, common practice, okay, for column, for column, for standing column with height, with the ratio height to diameter bigger than 10, is it is advisable to investigate effect of vortex shedding. All right. Okay. So how the common practice, how they solve it. All right. An example of this photo is taken from this website. Okay. Is by using helical strakes. Okay, we know that chimney normally has to be high in order to avoid air pollution to the human, to the living things. So uh, the design of chimney is high, and then of course it may have a wind induced vibrations, and it can cause failure to the chimney. So commonly what engineer do is by attach the helical strakes or strips also. So this you can see from here, there is a helical strakes. All right. And then for column, normally engineer will install ladders or pipes or platform around the columns. Okay, by putting this on the columns, on the column wall. All right. Uh, it can change the pattern of vortex shedding. Okay, it can change the patterns of vortex shedding, and thus it will prevent resonant oscillations. All right. Right. Earthquake loading. Okay. Now we move to the next topic on the earthquake loading. So we know that earthquake can cause a movement on the Earth's plate. Okay, Earth's surface. So when this happen, it's actually produce horizontal shear stress on tall vessel, especially to the tall self-supported vessel, and then the magnitude will increase from the base outwards. Okay, the magnitude will increase from the base outward. So basically, this equation is used to approximate the force on the vessel due to earthquake, where the constant AE is acceleration of the vessel due to earthquake. Okay, the term AE. Okay, and then G is for gravitational accelerations, and WV is total weight of the vessel and contents. So actually, okay, where's my pen? Actually, the constant of AE over G, okay, this is called as CE. Okay, CE, where CE is actually the seismic constant. I think this can easily be found if you search at Google. All right. And this causes a natural period of vibration of the vessel and the severity of earthquake. So we can use as can find the CE. And then the data for this seismic effect, all right, is available for some geographical location that have a frequent earthquake issue, and then you can try find it from you can try to browse from the internet, right? Okay, eccentric loads. Okay, eccentric loads. Eccentric load is for this. All right. The bending the bending moment due to heavy. Okay, this is due the eccentric loads. Okay, from here we need to calculate for bending moment due to heavy additional equipment attachment. All right. So example of heavy equipment attachments such as reflux condenser, side platform. Okay, all right. And then this is a calculation in order to find the dead weight of the equipment. All right. Sorry, sorry, not the bending moment. Okay, the bending moment, the eccentric loads, or due to heavy additional equipment. Okay, eccentric loads. All right. So, how the why this is important? Okay, some equipment is for example like distillation column, it will have a reflux condenser on the top of it. All right. So example of the fittings, like let me draw here. Okay, if let's say this is your distillation column. Okay, all right, and then it has an attachment of condenser. All right, just draw a simple shape to represent a condenser. Why it's important for us to okay, the central line of the distillation column and the attachment equipment attached to it. So we have here is the LO, and here we have the this is the one that we want to calculate the bending moment, and for this part, all right, is the weight of the equipment. All right, the weight of equipment. So the additional equipment, okay, the additional equipment or other term for this is commonly used is ancillary. All right, ancillary equipment. So the ancillary, all right, that attached to a distillation column or any tall vessel, all right, it was subject to bending. Okay, it was subject to bending due to the weight of this condenser or or any other equipment. Okay, normally a heavy equipment lah. So if the center of gravity of the equipment, okay, if the center of gravity of the equipment does not coincide, it's not the same with the center line of the main column, okay, or the main vessel, and then this will cause bending, okay, the bending moment, okay, load due to the bending. All right. So but the moment caused by such as ladders, pipes, manways, right, generally are small and normally are ignored, all right, neglected. Okay. Then for torque, okay, for torque, okay, torque may occur due to horizontal force from ancillary equipment, again from ancillary equipment, from additional equipment. For example, like when wind pressure acting on attachment and piping, okay, wind pressure push the attachment of equipment that attach to the columns or to the vessel, the tall vessel or piping. All right. So generally torque is small and can be neglected, but you must remember that whenever you design, you must consider that design that can reduce. Okay, the design that can reduce the load from ancillary equipment. All right. So class, that's it for now. All right. We'll continue next on the support. Okay. Next topic will be on the support of the vessel. Okay, load from the support of the vessel and the type of the support for the vessel. That's another critical things need to be considered. Okay, class. All right. See you again. Okay. We'll see you again. We'll see you again. And then please keep safe, stay safe. All right. Okay. Bye.